Hello, once again, and today we're going to look at, or in this video, we're going to look at rational functions. Now, our basic objective here is just going to be to, first of all, define what rational functions are, and then look at some of the basic characteristics of rational functions, things such as the domain, and some of the graphical characteristics of rational functions. And then we'll look at how to identify these characteristics. And from there, we'll look at some ways that we can sketch graphs of rational functions. So let us go ahead and begin by defining what a rational function is. So we say that a rational function is any function that has the form of f of x equals p of x over q of x, where p of x and q of x are polynomial functions. Simply put, a rational function is just a fraction containing polynomials. So the numerator and the denominator must be polynomial functions. So some basic examples of rational functions. We have here f of x equals 4x plus 2 over 2x minus 5. F of x equals 3 divided by x squared minus 4. And then f of x equals 2x squared minus 3x plus 2 over 2x minus 1. Now, we'll be using these examples in some of the slides ahead so that we can recognize some of the basic characteristics of the rational functions. So now, of course, as with any type of function, one of the things that we're oftentimes going to be interested in is determining domain and range of a function. Now, remember that the domain consists of the set of allowable x values in a function. The range is basically the set of y values. Now, identifying the range of a rational function can be somewhat challenging, but the main thing that we're going to look at or focus on is the domain. So to find the domain for a rational function, it's really simple. Since a rational function is just a fraction is the division. One number that we cannot divide by is 0. So we do not want to allow any values for the variable that will make the denominator 0. So simply put, the domain will be all real numbers except those values that make the denominator 0. So now, if we take a look at each and every one of the examples that we have laid out here, for the first one, we have 4x plus 2 over 2x minus 5. So now if we look at the denominator, 2x minus 5, and we set that equal to 0, we solve this equation, add 5 and divide by 2, we have x equals 5/2. So now, since this is the value of x that makes the denominator 0, the domain would be all real numbers except 5/2. Now we could also write that in interval notation. As the interval from negative infinity to 5/2 union 5/2 to positive infinity. For our second example, 3 over x squared minus 4, we basically go about it the exact same way. So here we have x squared minus 4, we set that equal to 0. Add 4 to both sides, x squared would be equal to 4. And we take the square root of both sides. So remember, when taking the square root of both sides, we have both a positive and a negative square root. So here, positive and negative 2 will be the values that make the denominator 0. So the domain here is going to be all real numbers except positive, -2 and +2. Now the interval notation here gets a little bit cumbersome. We have -infinity to -2 union -2 to +2 union +2 to +infinity. And the more restrictions you have on the denominator, the more convoluted the interval notation is going to be. But it's pretty much stating the same thing. All real numbers are allowable except for +2 and -2. For the last example, 2x squared minus 3x plus 2 over 2x minus 1. Now, we don't care about the numerator as far as the domain is concerned, because a numerator of 0 is just going to make the fraction equal to 0, assuming the denominator is not equal to 0. So the only thing we have to worry about is any value or values that make the denominator 0. So adding 1 dividing by 2, this will give us x equals +1/2. And so the domain here will be all real numbers except 1/2. Whose interval notation would be -infinity to 1/2 union 1/2 to +infinity. All right, so once again, for the domain, all we have to worry about is taking the denominator, setting it equal to 0, and solving it. The solutions that we get there will be the restrictions the solutions will be the restrictions, and the domain will be all real numbers except those restrictions. Now, let's begin to take a look at the graphs of the functions. So I'm going to take a look at the graphs of these functions. If you have a graphing calculator, you can graph these out on your own. But I want us to take a look at what these types of equations look like. When we begin to study functions and different types of functions for the first time, we might be interested in finding out if there are any common characteristics amongst any particular class or group of functions, and then how we can use those commonalities to help us to sketch graphs of these functions and also determine other types of characteristics of these functions. So now here we have a graph of the first example, 4x plus 2 over 2x minus 5. Right? And so you'll see a couple of things that are interesting here when you look at the graph. Unlike polynomial functions, which had a tendency to be continuous and flow throughout the set of real numbers, because polynomial functions have a domain of all real numbers, we see there are some interesting things that are happening here. The first thing that you might notice is that the graph seems to do something a little bit strange here at the value of 2.5, which was 5/2. Now, if you recall from our discussion earlier, that was a restriction of the function. That is to say that the function was defined for all real numbers except 5/2. And so now we see that we don't have a function value for 5/2, but look at the behavior function as we approach 5/2 from either side. As we approach it from the left, the graph is decreasing without bound. As we approach it from the right, the graph is increasing without bound. Now, whenever this happens, this type of behavior, whenever we have this type of behavior, this vertical line is what we refer to as a vertical asymptote. So we have a vertical asymptote here at 5/2. Now, something else that's also interesting is that with a little bit of observation, you may also notice that the graph tends to display a similar type of behavior with respect to a horizontal line. Here it appears to be at +2. Now, when it happens in the case of a horizontal line, we would refer to this as a horizontal asymptote. Now here, it appears as if the horizontal asymptote occurs at 2. We can't be quite sure, but there are ways that we can be definitive about that, and we'll get into that a little bit later on. All right, so we have a vertical asymptote at 5/2. A horizontal asymptote looks to be at the value of 2. So now let's look at the next example. Next example, 3/x² minus 4. Now here we see a couple things. First of all, taking a look at the values, remember here the restrictions were at -2 and +2. At -2, we see that we can identify a vertical asymptote, and the same thing at +2. So now one thing we can already establish here is that we seem to see these vertical asymptotes at the values where the denominator is equal to 0, at the restrictions of the function. So that's something that we probably want to keep in mind and make a note of for later. We can see also the graph as x increases without bound, as we move to the left, as it decreases without bound, also as it increases without bound, that the graph tends to flatten out and approach the x-axis. So just like we noticed in the previous problem, it appears as if we also have a horizontal asymptote, in this case at the x-axis. Now, if we take a look at the third example, we'll see something rather interesting here. 2x² minus 3x plus 2 over 2x minus 1. Now recall, for this particular function, we did have a restriction at 1/2. And so upon closer observation, we can see that there is definitely going to be a vertical asymptote at 1/2. But now note here, unlike the other two examples that we looked at, when we look at the end behavior, what's happening as x increases or decreases without bound, the graph doesn't tend towards a horizontal line as we saw in the previous example. In this instance, it appears to approach a slanted line. So what we have here is what's referred to as a slant or an oblique asymptote. So the end behavior doesn't tend towards a horizontal line, but it tends towards this slanted line. So now we have this possibility that some of these functions may have non-horizontal asymptotes. Now, when we look at each of these graphs, obviously what we can see is that the asymptotes are going to play a major role in the behavior of the function. But now, what are these asymptotes? What are the asymptotes about? Well, the asymptotes in these instances are going to be lines that the function will approach but doesn't cross, which is the case for vertical asymptotes. We notice in each of those cases, as the function approaches a vertical asymptote, it either increases without bound or decreases without bound. Or it can be used to describe the end behavior of the function, which is something that is the case for the horizontal asymptotes or the slant or oblique asymptotes. We see that with those asymptotes, they kind of give us an idea of where the function is going as the x increases and decreases without bound. But in each one of those examples, the graphs themselves were pretty much guided by the asymptotes. All right. The asymptotes served in more or less a sense, they served as boundaries to the function themselves. So if we can identify the asymptotes, the vertical asymptotes, horizontal or slant asymptotes of a rational function, that will give us a lot of insight into determining what the graph of a rational function is going to look like. So now, of course, the next question is, how do we find these asymptotes? And then how can we use the asymptotes to graph rational functions? So now let's talk about how to go about that process. So let's say we start with a simplified rational function. Now, I use the term simplified here, and this is something that I want you to keep in mind because when I say simplified, what I mean is that there's no common factor between the numerator and the denominator of the rational function. So if we have a simplified rational function, to find the vertical asymptotes, well, that's very simple. We saw that what we observed in the graphs was it was just a clear matter of where the denominator is equal to 0. So the vertical asymptotes, we set the denominator equal to 0, and we solve the equation. Once you solve the equation, the solutions will be the vertical asymptotes. Now, later on, we're going to do some examples of the rational expressions where we'll see this process play out. To find the horizontal or slant asymptotes. Now, this is a little bit more complicated. All right, so there are a number of different steps that we have to look at. So the first thing we have to look at is we have to look at the degree of the numerator and the denominator of the rational function. So we have three possible outcomes there. Either the degree of the numerator will be less than the degree of the denominator, the degree of the numerator will be equal to the degree of the denominator, or the numerator will have a higher degree than the denominator. Now, in the case that the degree of the numerator is less than the degree of the denominator, the horizontal asymptote will simply be the x-axis or the line y equals 0. Now, that we saw manifested with our function f of x equals 3 over x squared minus 4. In this particular problem, the degree of the numerator is 0, and the degree of the denominator is equal to 2. And so we have, and so because we have a smaller degree in the numerator than in the denominator, you can see the end behavior of the function tends toward the x-axis. The second case If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is going to be a line that is going to be the line y equals the quotient of the leading coefficient of the numerator divided by the leading coefficient of the denominator. Now, this was something that we saw with the second example. I'm sorry, with our first example, that is, 4x plus 2 over 2x minus 5. Now, if we take a look at the numerator and the denominator, both the degree of the numerator and the denominator is equal to 1. So the horizontal asymptote, we take the leading coefficients and we divide them. So that'll be 4. That's the leading coefficient of the top. The bottom has a leading coefficient of 2. So 4 divided by 2 is going to be equal to 2. And so then, if we recall, if we look at the function itself, y equals 2 was in fact our horizontal asymptote. All right, so if we have equal degrees, divide the leading coefficients to get the horizontal asymptote. In the third instance, where we have a higher degree in the numerator than in the denominator, in this case, we'll have a slant asymptote. So now, how do we find the slant asymptote? In this case, the slant asymptote will be the quotient without remainder of the numerator and the denominator by long division, or if it's possible, using synthetic division, depending on what your denominator is. So this is what we saw in the third example. We had a slant asymptote. So now let's take a look at what the slant asymptote would be here. So as I said, the slant asymptote is going to be found by dividing the numerator by the denominator. So now in this case, we'll use long division. So we got 2x minus 1 divided into 2x cubed minus 2x squared, minus 3x plus 2. So now, if we go through the polynomial division, we look at the first terms, 2x into 2x squared, it's going to be equal to x. Multiply x by 2x minus 1, that's going to be 2x squared minus x. And then we subtract. 2x squared cancels out. Negative 3x minus negative x, that'll be minus 2x. Bring down the next term, plus 2. 2x into negative 2x, be minus 1, or negative 1. Multiply negative 1 by 2x minus 1. We'll have 2x, or negative 2x plus 1. We subtract. 2x cancels out. 2 minus 1 is equal to 1. Now, 1 is our remainder. We ignore the remainder. So, in this case, the slant asymptote will be the equation y equals x minus 1. All right, and so this line we can actually draw on the graph. So if we plot the points, x minus 1, we have a y-intercept of a y-intercept of 1 and a slope of 1. Y-intercept is negative 1, that is. Okay, and so if we draw the equation of that line, we see it looks something like this. So once again, noting that those asymptotes pretty much drive the behavior of the function itself. All right, so now we'll take a look at how we're going to use all of this information in order to graph or sketch the graph of rational functions. And so we're going to do that in the next part of this video. I don't want this one to run too long. We've got the basics down about rational functions, what they are, how to find the domain, and how to identify the asymptotes. So in the next video, we'll talk about the steps involved in graphing rational functions, and we'll look at a couple of examples of graphing rational functions as well.